electron transistor.
Excuse me, sir.
Yeah. Yes.
Hello. Yes. So can you take the tangents once again, sir? I joined late, sir.
Okay. Yeah. Right. So we have been discussing Coulomb blockade and single electron transistor. Okay. So let me briefly recapitulate whatever we have discussed. We have considered that uh, did I switch on the video recording? Okay, it's done. Okay. So we mentioned that we need very small capacitor of the order of autofarad, okay, to see this Coulomb blockade effect, which is nothing but um, you need an appreciable amount of energy so that you can transfer even a single electron, or you can tunnel a single electron from one plate of the capacitor to the other plate. And we did find out that an expression for that, and it was uh, V greater than QE over 2C, where QE is the charge of a single electron, right? And corresponding energy should be greater than QE square over 2C, right? So this is the charging energy of the capacitor, and this is the basically the voltage you need so that uh, you can transfer a single electron, right? And correspondingly we have found out some of the expression uh, which is associated with temperature, because we said that if the capacitor value is a bit large, then we need much lower temperature to see this effect, right? And we did mention that if we can control this precisely the movement of even a single electron, um, then our device will be very accurate, and we can develop a device which is basically nothing but a single electron device, okay, where we can control even a movement of single electron. And correspondingly we develop a model which is nothing but what we usually use for a lump capacitor, where we said like the model can be an ideal capacitor with a leakage resistor, okay, and this leakage resistor from Heisenberg uncertainty principle, we said that it is of the order of 25.8 kilo ohm, right? And the corresponding symbol of this such tunnel capacitor is like this, okay, we will designate as TJ, that is the tunnel junction. Then we talked about a uh, quantum dot or quantum island, that is a small nano island, okay, and that small nano island, there are two contacts close to this nano island, okay, and it is driven by a voltage source, right? This is what we have discussed. And this quantum nano island or quantum dot, okay, um, what we intended to do in the last class is to find out the condition, similar condition, or the voltage you need or the energy you need so that you can transfer a single electron from one contact to this quantum dot and this quantum dot to another contact, so that you can get a current through the circuit, right? And what should be the voltage or what should be the energy associated with it, so that you can transfer even a single electron precisely, right? And let me just briefly mention the relations. So this is one tunnel junction and we represented as TJA, and the corresponding voltage was VA. This is the quantum dot, and there is another tunnel junction, that is say TJB. Okay, the corresponding voltage was VB. So this was our basic circuit, right? Um, and we the total energy we wrote, this is again very easy. So this is total stored energy. Stored energy is CAVA, half CAVA square. Okay, sorry, plus half CV VV square. And you remember we found out the values of VA and VV, okay, in terms of this VS, okay, because VS is known, and we found out VA and the corresponding VV, similarly 1 by CS over VSCA my plus NQE. What is QE? QE is the charge of the electron, and N, if we consider there is n number of electron present in the quantum dot, right? And from there we said, like, if we transfer one electron from junction B to the quantum dot, how the relation will look like, and we ultimately found out uh, the total total energy, change in total energy, right? So we can we did put VA and VB value here, and we got this energy E, or the stored energy EAC, as this, okay, CACB Vs square plus NQE whole square. Okay, so that was the stored energy. Now we argued that let's assume that the one electron tunnel from junction B to this quantum dot. Okay, if this is the case, then what will be the change in total energy? So this is the stored energy. We can write change in total energy, okay, in the same form. So this is, you see, the stored energy 1 by 2 CS CACB Vs square plus NQE whole square. Okay, so that is what we are writing here, CACB Vs square plus NQE whole square. Okay, so that's my initial energy. Then when one electron is transferred, then the energy will be n plus 1. Okay, so n plus 1 QE whole square. Okay, because it was n number of electron and one electron is transferred to the island, so the island number of electron becomes n plus 1. Okay, and this minus Vs Ca QE over Cs. So that's the change in total energy. This term is the work done by the supply voltage, right, that we mentioned yesterday in the last class. So this has to be greater than 0 to make this phenomena energetically favorable. This is the similar things we have used in the last class. You remember, for the simple parallel plate capacitor. And if you use this, you ultimately will get Vs greater than minus QE over Ca n plus half. Okay. um, in a similar way, when an electron tunnel of the island through the junction A. Okay, so this is the condition when the electron tunnel from junction B to quantum dot. Now I am saying quantum dot to junction A because ultimately, if you want to get the current, the electron must travel through the whole circuit, right? So if quantum dot to junction A, if the electron travel, okay, or tunnel through, then similarly it is possible to show, okay, similarly it is possible to show that delta Et, okay, you can write this similar expression, right, and greater than 0, in this case quantum dot to junction A, and here it is junction B to quantum dot, right? So in this case it is possible to show that Vs should be greater than Qa over Cb n minus half. Okay, so it is possible. I'm just keeping the steps. You can see my note which I have uploaded already in the MS Team. You can see the steps, but it is the similar steps you follow, and you assume that the total change in energy is greater than 0 to allow the phenomena to happen, and you will get this, right? Now if you have this Ca equal to Cb, and then, and if you consider this n equal to 0, that is no electron was there previously in the island, then you will end up with Vs greater than QE over 2C, right? So if you consider n equal to 0 and Ca equal to Cb in this relation, you will get Vs greater than QE over 2C, the same Coulomb blockade relation as we encountered for a single capacitor case. Okay, right? Now the thing is, assuming one electron has already tunneled on the island, okay, if we consider another electron, so if we make things little bit complicated, so so far we have discussed that junction B to QD, and then QD to junction A, the electron travels, right? Now instead of doing that, if we say that one electron travel from Q to from B junction B to QD, and then a second electron travel from or tunnel from junction B to QD, okay, then what will be the energy situation, that also you can write exactly in the same fashion. Okay, like if you remember, we wrote 1 over 2 Cs Ca Cb Vs square, plus in this case it will be n plus 1 because n plus 1 electron already exists. Okay, so that is minus 1 over 2 Cs Ca Cb Vs square plus n plus 2, because first electron is there and you are now transferring another electron. Okay, minus Vs Cs Cb, sorry, Ca QE over Cs. Okay, so that's the work done by the supply voltage. So this is the case when we transfer, or a single electron transform from junction B to quantum dot, and again another electron transfer from junction B to quantum dot. Okay, so this, if you say that this is to make this energetically favorable, and you ultimately will get expression, if you follow that, you will get expression n plus 3 by 2. Okay, so here you see it was n plus half, now it is n plus 3 by 2. Okay, so that is again you can consider Ca equal to Cb is equal to C, and considering the tunnel direction, we ultimately got the similar expression where it is 3 QE over 2C. Okay, similarly we can get if we assume that there is third electrons transferring from quantum I mean from junction B to quantum dot, we will get Vs greater than 5 QE over 2C and so on. Okay, so it is ultimately that Vs for the m electron, okay, Vs should be m QE over 2C, right? So we can, so here m is basically 1, 3, 5 and so on, right? So this is I mean you can plot we can plot uh, I over I1 versus Vs over V1. Okay, and we will get curve something like this. Sorry. So here this is basically your 2, this is 4, this is 6. Okay, so you see so this V1 is nothing but QE over 2C, and I1 can be shown is QE over RTC. You remember RT is that leakage resistance we mentioned previously. So you see here m can be 1, 3, 5 etc. To get current through the through this particular device, right? Thus electron tunneling event given can only happen when m equal to 1, 3, 5 etc., giving rise to currents. Okay, and that will occur at discrete voltage steps, right? At discrete voltage steps. um, so now we, so far we haven't considered uh, any transistor. We just talked about, we have a quantum dot, two metal contacts at the two end, okay, which is basically creating a capacitor structure. There is one capacitor from quantum dot to one junction, and another capacitor from quantum dot to another junction. So there are two capacitors, and in between sandwich there is a quantum dot, and we are applying a source, that is a supply voltage, and seeing the movement of electron tunneling through these junctions to quantum dot and quantum dot to another junction, so that we can get a current in the circuit, right? And we found this condition that there is a voltage required Vs greater than m QE over 2C and m135 and so on, and in this discrete supply voltage we will get a current. Okay, and this is known as, this staircase representation is known as Coulomb staircase. Okay, so it is known as Coulomb staircase, right? Now the thing is, we can now consider a third terminal, because a transistor, we know that it is usually, transistor is a three terminal device. So we will have a gate terminal also. Okay, in the gate terminal, if we now consider a transistor, so again let me redraw. This is my quantum dot. I have two contacts. Okay, and I have a, say I have a insulator with a contacts here. Okay, and sorry,
Excuse me, sir.
yeah,
Sir, in that expression which you have derived,
right,
that condition for Vs,
right.
Sir, I have cross-checked that and I was getting it to be minus 1 upon Ca in bracket n plus QE by 2. Even I have sent you the steps on mail.
You have sent me the you have sent me mail.
Yes,
Mm,
sir. Last week.
uh, which is so you are saying this expression QE over
In
CA.
previous slide.
Sorry.
In previous slide.
Yeah,
Yes, sir. Here. That
right.
expression that Vs greater than minus QE by Ca, it
Mm.
was coming out to be minus 1 by Ca in bracket n plus QE by 2. And similarly for the next expression, it was 1 upon Cb n minus QE by 2.
Okay, so you are getting QE inside,
Yes, sir.
and it was 1 by CA and it was 1 by CB. That is what you are getting, right?
Yes, sir.
Uh, okay, right. Okay, so in that case, I will double check it. I will double check and then reconfirm you. Okay,
Yes, sir.
right. What is your name?
Sir, Gurmeet Arora.
Okay,
Yeah.
okay, right. Okay, thank you. Yeah, right. So uh, so this quantum dot, okay, this quantum dot. So Gurmeet, did you see my note which I uploaded?
Yes, sir. In that note, when you have taken QE common, then in that case, one term was QE square and one term was QE. So you have considered QE plus again QE. Means I have checked your
Okay,
note also.
okay.
Yeah.
I will double check that. Right.
Yes.
Okay, I will double check that. So um, so this so this is my uh, transistor circuit, where you see I have a quantum dot, okay, as usual as before. We have two contacts, okay, but now we have a like a insulating layer and a metal contacts and I have a gate voltage, right? There should not be any current flowing or any electron flowing through this insulating layer, but electron should depending on the voltage, electron can flow or tunnel through from this junction to quantum dot and then quantum dot to another junction, right, as usual as we discuss things before. So so if we here also again we can consider that say QA is equal to CAVA, QB is equal to CVVB, and QG is equal to CG VG minus VB. Okay, so these expressions these are pretty straightforward, and we can assume this expression, and we can also find out E stored energy of these three capacitors, okay, and also we can so we can find out half CAVA square plus CBVB square plus CGVG square, etc. We can write in stored energy form, okay, and the exercise we carried out already, we can do similar exercise uh, to find out the condition for which the electron will tunnel from one junction to quantum dot and then from quantum dot to another junction, okay. So that will, I'm again skipping a lot of steps because I just wanted to show you the what is the implication of that, or how what it ultimately represents. So again, you can see the note and follow those steps. I'm just skipping those steps, assuming that if we follow the note, you will be able to figure out and come to the ultimate expression. So what I am doing here, that when a charge tunnel across a junction, we are finding that delta Et, okay, say delta Et greater than 0, and in a similar manner for an electron on the island to tunnel off the from island to junction A. Ultimately this will give you the expression which is Vs greater than 1 over Ca minus QE over 2 CGVG. Okay, so this is the expression you will get if you follow steps of similar thing which we have discussed already. Now now the thing is, if we plot this, if we plot this, we will, what we will get, we will get, let me go to next slide. Okay, so we will get Vs over Vg, okay, and this is minus QE over 2Cg, and this is minus QE over 2Ca. Because you see, if you see this inequality, there is minus QE over 2Ca and minus CgVg over Ca. Okay, so you can you will get get this. Okay, similarly if you do the if we assume that we already have one electron at the island, and then another electron tunnel onto the island through junction B, exactly the same thing what we have done before. Okay, we will have like so one electron was there from B to QD, again we have another electron from B to QD. We will get Vs, okay, Vs greater than, and you can plot, again you can plot this, okay, and you will end up with, so this inequality shows that this is, I think there must be a Ca term here, there must be a Ca term here, right? You can you check this, I think there must be a Ca term here. So again if we plot this inequality, okay, we will get expression of this, we will get plot of this sort, where this is QE over 2 CB plus CG. Okay, here also I am plotting Vs over Vg, and this intersection will be minus QE over 2 CG. So to get to get current out of to establish current, both this inequality has to be valid. Okay, so we end up with so we have seen two cases. One is where the voltage, where the electron tunnel from QD to quantum dot, and another case is from quantum dot to QA or junction A. Both this condition has to be valid to get current. Okay, So this is the window where you will get both this. If we follow the inequalities, we will see to validate or to get current, this is the zone. Okay, now you can or we can have similar things following. I think I have um, um, I'm just skipping again some of the steps and assuming that there are, if we have like instead of one electron inside the quantum dot, another electron is coming, then the electron is going to the junction A, and if there is two electron, the third electron is coming from junction B to quantum dot, again it goes to junction A, and so on. If we follow that, we will ultimately end up with lots of inequalities, similarly what I tried to mention now, and we will see that it is possible to draw a similar diagram what we have drawn already. Okay, uh, and uh, we will get lines like these. Okay, um, so it is possible to show that that there will be no current here. Okay, so current is so you remember, if you look at here, we see we got current in this region. Okay, so this is the portion which is here. Okay, similarly here. So this so when m, so we can write Vg is equal to mQe over 2Cg. Okay, so this m equal to 1 plus minus 1 plus minus 3 plus minus 5 etc. There is no Coulomb gap and one can get current very easily. Here you see one can get current very easily for very small values of Vs. You see, this is y-axis my Vs. So very small values of Vs you will get current. Okay. On the other hand, when m equal to 0 plus minus 2 plus minus 4 and so on, in these cases you will not get current. So this is say m equal to 0, m equal to 2, m equal to 4 and so on. In these cases there is maximum Coulomb gap, and that gap must needs to overcome by the supply voltage, then only you will get current. Okay, then only you will get current. So this particular diagram is known as Coulomb diamond. Okay, this is a stability diagram, right? So all what I wanted to draw in this particular plot is we have got two inequalities. One inequality is for tunneling from junction B to quantum dot, and another inequality is from quantum dot to junction A. If both these situations simultaneously valids, then we will get current through the circuit, and that particular inequality zone is this portion, right? Because you remember one portion was like this, okay, and the other portion was like this. So the common portion is this part where we can get current, right? So this is for one single electron. Okay, we can have, as I mentioned, like we can have like multiple electrons. Say I have n number of electrons in quantum dot, and then again one electron coming from junction A to quantum dot, and then from quantum dot to junction A. Okay, if you follow that, you ultimately will end up uh, with similar kind of inequality plots. Okay, where it is possible to show that for m equal to 1, 3, 5 and so on, for very small Vs you will get current, so there is hardly any voltage you need to get current. But when you have like m equal to 0 or m equal to 2 or m equal to 4 and so on, or plus minus, then you need appreciable amount of voltage, otherwise the current is zero. So this is a known as Coulomb diamond diagram or stability diagram. You see in this particular portion, the island charge in the island is quite stable and there is no tunnel, right? Once you move from here to here, then it is easier for the electron to tunnel, because this is simply we are achieving this because of the gate voltage we are applying at the gate terminal, right? um, I think I'm stopping it here. Um, I think most of the steps are very uh, elaborately written in the note. You see the note, but I don't want you to expect to memorize this step. All what I want is you go through the note and try to understand what is a single electron device, how this single electron device might work. To be honest, there is no commercial device like this. People manage to fabricate such device in the lab and manage to demonstrate this Coulomb diamond or Coulomb staircase effects. But you see, you need extremely small capacitor to achieve such a device. Okay, and also you need otherwise you need quite low temperature. So this kind of device is still not available commercially, but it is there are lots of paper works, I mean the lots of paper published in journals about single electron transistor, about single electron devices and how these devices works and so on and so forth. But as you understand, there are a lot of constraint. You have to have a very small quantum dot with a very tiny junction, so that you can get a very small capacitor. So this kind of fabrication is not easy to do. So it is not easy to make these devices batch fabricated. So what I mean is, it is not easy to have like such devices with large numbers. Okay, and such reliable devices with large numbers, like, so all the devices are performing in the same fashion, so it is difficult to achieve. So that is why there is no the commercial device of such a type. But as I said, like, people have already demonstrated in their lab that it is possible to make such devices. Okay, with fair amount of accuracy and achieve this kind of characteristics. Now, before I forget, I want to mention, like, that this the NSEM exam will be offline, right? You know that, right? Hello.
Yes, sir.
Right.
Yes, sir.
Right. So now, what I want, like, I want to take a quiz or MCQ type MCQ type quiz in Moodle uh, sometime soon. So because we haven't, so I have take one exam. We will take another exam in the form of NSEM I couldn't this time. I couldn't take exams because I used to take two more class tests, so that somehow I couldn't do. So what I want, like I want to take a small quiz in Moodle, MCQ type. So I want to know, like, which day will be favorable for you. Um, so at the end of March, is it possible?
Many of us will be traveling at the end of the March. So, uh, like the deadline to reach the campus is 31st of March. Many of
Right,
us have got the tickets around 30-31.
right.
It will be like uh, if 31st March evening will be like fine, or 1st April onwards, any day.
Sir, maybe you can take it on 22nd, 22nd is better.
22nd means next week Tuesday, right?
Yes, sir.
Possible, please take it after 31st of March.
Yes, it's also fine, sir.
31st of March. Okay. After 31st of March means after 31st of March means 4th of April, right? 4th of April is Monday, right? Either 4th or 5th.
So, what would be the syllabus then?
Uh, mm, See, whatever I am covering after mid-sem will definitely be there. So what did I cover? Could you please, just a second, could you please remind me what, give me a second. Yeah. So could you please remind me what did I cover after mid-sem?
Sir, you have covered after midsem tunneling, then double barrier case of tunneling, and then nanofabrication, then lithography, then quantum dot, that is single electron transistor and Coulomb's blockade, and whatever you have covered today. That much.
So okay, so I have covered tunneling, I have covered RTD, I have covered very briefly nanofabrication, means photolithography and e-beam lithography, and now I have covered uh, Coulomb blockade, single electron transistor, right? Right. And before mid-sem, I have covered IC roadmap. I have covered FinFET. I have covered quantum mechanics. Is that so? Within quantum mechanics, there is photoelectric effect. There was de Broglie. Then there was Davison-Germer experiment. There Schrodinger and so on. Right? Is that all?
Hampton HBT.
Right. I have covered Hampton HBT. Hampton HBT. Right. Okay. Right. Right. Okay. So, um, so let's exclude Hampton HBT. Okay. Um, let's exclude Hampton HBT part from the for the NSEM syllabus, right? So rest of the things will be there along with whatever I'm going to cover. So how many classes I will have after this? Today is 14th, right? Today is 14th. So there will be 15th. So 1 hour, 21st, 22nd is 3 hours. And 28, 29. So 3 plus 1, 4. 4 plus 3, 7 hours. So NSEM will start from when? From 7th?
Yes, sir.
7th. So do you want me to stop on 29th of March?
Yes, sir. Yes, sir.
Then we will take exam on 4th. 4th the quiz. Is that okay?
So then, this quiz is the NSEM, or you'll have another NSEM exam written?
No. This is not NSEM. NSEM is written, right? NSEM is written test. Right? That is the institute decision that NSEM will be written test. I think
So,
2
sir,
hours.
will you be like fine with taking quiz syllabus as post class test one, and then the NSEM syllabus will include all like FinFET and other things, excluding HEMT and HPT?
I mean, I can do that. The only thing is because it will this 4th is too close to that of the NSEM. So anyway, you will study the whole thing, right? So and it is nothing but an MCQ. You will have like you will have 3 or 4 answers. You need to tick one, something of that sort. So I prefer to include everything except Hampton HBT so that your preparation is complete. So this will be a small quiz, maybe for half an hour or so, or maximum 45 minutes. That I don't know, because I need to talk to Moodle and see if I can get a slot and all that. Because anyway you are going to study the other parts, I mean the before mid-sem parts also, and it is very close to end-sem. So I prefer to include those so that your preparation is complete. Okay.
Sir, will answer be similar to our first test? Like 5 questions will be there and
That I don't know. I need to see like what is the duration and all that. I am not sure like what I need to see what is the because if it is like 2 hours, then that 5 question will not be probably will be very small. Understand what I'm saying? But the type will be of similar type, but it may be more questions depending on the duration. The duration exactly I don't know at the moment. Okay, so we'll see how it turns out, but I will let you know. Okay.
Sir, will the question be in the same line, like explain in 2 or 3 lines?
Yeah. Question will be of similar line. Okay. um, because if you see my earlier, do you have like earlier questions? Do you have earlier year questions?
No, sir.
Okay, I can share that with you. You will see that more or less all the time I am giving questions like brief questions, maybe maximum 4 or 5 marks if it is at all at that length. Otherwise, like 2 3 marks question, maximum 5 marks for a single question. So I always do that way, but uh, you have to answer, but if someone sets up question in that form, then you have to answer a lot, not like lengthwise, but maybe volume wise, because a 10 marks question and 3 marks question is different, right? So you have to write, you have to cover a lot of volumes. Let's put it this way. But you have to be brief so that you can manage to finish them within the stipulated time. Anyway, so let's we will have class till 29th of March. On 4th we will have a quiz. Let me see, 4th or 5th. Once I book the slot in Moodle, I will let you know. Okay. Right. So give me just a few minutes break. I will uh, start a new thing now. Just give me 2 3 minutes break. Okay, it's coming from washroom. Thank you.